Hello out there, you are welcome to Deep Truth Academy, where we are devoted to building excellence in STEM education. In our video today, we are going to be looking at one of the past questions from the physics exam paper offered by WAEC, and we are going to be considering the 2019 objective exam paper. So we are going to look at all the 50 questions. We are going to give a detailed solution to them. We are going to explain the options, why we are picking the correct ones, where we could have made some mistake in picking a wrong choice, and the best way to also solve our calculation problems. I want you to get set. Our work is drawn out for us, and I know this is going to go a long way to help you gain that academic excellence that you are aiming for. What we just want you to do before we proceed is, if you are here to subscribe, go ahead, click on the subscription icon, click on the notification bell, so that anytime we are uploading our videos, you are going to have access to them on the fly. And don't forget to help us share the video on your social media platforms, on your Facebook, on your WhatsApp, on your Twitter, on your Instagram. We want to build academic excellence in students, and that is the contribution that we are soliciting, that you also help in achieving this mandate together. So without much ado, let's head to our video for today. In this question, we are being asked that the time rate of increase in velocity is called what? Is it force, momentum, acceleration, or speed? If we try to look at the definition of what we are giving here, we are told that the time rate, and every time we are talking about the time rate, that is saying something like we are dividing something with time. And what we are dividing here is the increase in velocity. Okay? This is what we are dividing. Increase in velocity will mean that we have a change in velocity. Okay? So if you are to interpret that in physics, you can say this is something like a change in velocity, then we have the final velocity minus the initial velocity over the time t. And if you are very conversant with formula A in physics, you know that final velocity minus initial velocity over time is nothing but acceleration. Okay? Acceleration is defined as the rate of change of velocity with respect to time. So the correct option is option C. Acceleration is the correct answer here. In this question, we are being asked that which of the following quantities is a vector? Is it volume, momentum, energy, or speed? For us to be able to answer this question correctly, we should be able to know what a vector quantity is. Generally, quantities are divided into scalars and vector. So we have scalar quantities and we have vector quantities. Scalar quantities have only magnitude, meaning that you can find the value, we can quantify the magnitude, the amount of whatever it is. But vector quantities, they have magnitude and they also have direction, meaning that we don't just measure the value of our measurement there, but we also talk about the direction in which such a measurement is being applied. Now, looking at the options that we are given, here we have volume. We can measure volume in, say, liters and liters, centimeter cube, decimeter cube, but we know that volume is only a scalar quantity. Okay? When we are talking about speed also, speed is a scalar quantity, because if you want to talk about a vector quantity in that case, we are going to be talking about velocity. Velocity is a vector quantity because it is displacement over time. Displacement itself is a vector quantity. Speed is distance over time. So speed is also a scalar quantity. So the correct option is lying between momentum and energy. If you want to really understand which of this is correct, we need to break this down. Let's look at energy. What is energy? Energy is defined as force multiplied by distance moved in the perpendicular direction. And when you hear distance moved in the perpendicular direction, that means it's talking about displacement, because the direction is already being specified in that. Meaning that if you are looking at energy, we know that force is a vector quantity because it has acceleration embedded in it, and acceleration is a vector quantity. So we have a vector multiplying a vector. Okay? Now, in physics, this is actually a dot product of two vectors. And when you are talking about dot product of two vectors, what that is going to give you is going to be a scalar. That is going to amount to a scalar quantity, because dot products always amount to scalar quantity. It's like you're having the x component and the y component multiplying by the x component and the y component. What we have is something like s squared plus y squared, and that is a scalar quantity. Okay. However, if we are talking about the momentum is a different case scenario in which we are having mass multiplied by velocity. That's what we talk about when we're talking about momentum. And looking at this, mass is a scalar quantity, okay, but velocity, like I explained before, is a vector quantity. It's as if here we are having a factor to either multiply or divide to increase or decrease a vector quantity. So the product of a scalar and a vector quantity will always give us a vector quantity. And with this explanation for this particular question, the correct answer out of all these quantities that we are given, the one which is a vector is momentum. The mistake that students may want to do is to pick energy. No, energy is not the correct answer. The correct answer is momentum. In an elastic collision, momentum is conserved as well as what? Is it velocity, kinetic energy, potential energy, or speed? Generally, for elastic collision, what is being meant is that the net loss in kinetic energy is zero. So every time we are talking about a body or a set of bodies undergoing elastic collisions, we are saying that this means that loss in kinetic energy is zero. And of course, there are generally two formula here that we use to evaluate the parameters of bodies undergoing elastic collision. And the first case, we talk about the momentum. Okay. And for the momentum, we are saying that the sum of momentum mass times velocity before collision is the same as the sum of the momentum after collision. And then the other case is that we are talking about the kinetic energy. That the sum of the kinetic energy is half mp squared before the collision, okay, is the same as the sum of the kinetic energy after collision. So with this definition, looking at the options, what needs to be conserved alongside momentum in elastic collision is kinetic energy. So that's option B. The induced current in a coil always flows in a direction so as to oppose the change that causes it. This statement is known as what? Is it Coulomb's law, Lenz law, Faraday's law, or the Ampere's law? Now, let's have a holistic look at all the options that we are given, so that even if we are having this question in some subsequent exam, we'll be able to identify which is which and know the right answer to pick. And as a guide to that, I've drawn up a little brief which we are going to be looking at here now. So, in the first case, we are talking about the Coulomb's law, and the Coulomb's law is a statement of the force of attraction between two bodies of different charges or of the same charges, and is saying that like charges they repel while unlike charges they attract. Okay, so that's a statement of Coulomb's law. The like charges repel, but unlike charges they attract. So the force of attraction between two charged bodies is expressed by Coulomb's law, and it is given as the constant of proportionality multiplied by the product of the charges divided by the square of the distance between them. That is Coulomb's law in option A. In option B, we are talking about the Lenz law, but we are going to come to that later. Let's look at option C, the Faraday's law. Faraday's law is a statement that when the magnetic flux, which is linking a circuit, changes, an EMF is induced in the circuit, which is proportional to the rate of change of the flux. So now this is a magnet, and what we notice is that as the magnet is being moved forward and backward, what will happen is that there will be an induced EMF in this coil, okay, and the EMF induced is proportional to the rate of change of the flux that is producing it, the flux from the magnet. So that is the statement of the Faraday's law in option C. Now, in option D, we are looking at Ampere's law, which is a statement that the magnetic field created by an electric current, like here we have an electric current, the magnetic field that such a current will produce is proportional to the size of the electric current with the permeability of free space as the constant of proportionality. So that is why we are saying this current is proportional to the circumference of this wire, okay, which is expressed as 2 pi r, and the permeability of free space is the constant of proportionality. So this is the statement of Ampere's law. And looking at all this, I want to isolate them out so that we don't get confused with what Lenz law is talking about. Now, we're clear with this also. The Lenz law is actually a law that is riding on the Faraday's law. You know, we've talked about the magnetic flux that's being generated, which will also generate an induced EMF. But the Lenz law is talking about the direction in which the current will be induced, and that's why we're having this negative sign. So this is a statement of the Lenz law, okay? And what that means is that, look at this now. If the magnet, let me use the blue ink, if the magnet is being taken into the coil, what will happen is that the current that will be generated will be opposing the flow of that. So this will be the direction of the current. However, if the magnet is being taken away from the coil, then in that case, the current will move in the opposite direction also. So in this current in a coil always flows in a direction so as to oppose the change that causes it. Is a statement of the Lenz law. But if we come across any of these other laws in some subsequent exam, we'll be able to tackle them correctly now. And the correct answer to this question is option B. It is the Lenz law. Which of the following instruments can be used to compare the magnitude of charges on two given bodies? Without missing words, the correct option out of all this is the option C, the gold leaf electroscope that is being shown here. And what is normally the process that can be done to compare these two charges is that a charged body can be brought to the metal plate. The metal plate will ideally have some charges on it. So let's say these are some charges on it. And then the charged body is also coming with some charges. And the gold leaf is going to be deflecting, this gold leaf foil here is going to be deflecting to show the amount of charge that is being brought in contact with the gold leaf electroscope. Now, it is the amount of deflection that will determine the comparativeness of the two bodies that are being compared together. So the amount of deflection of this gold leaf will tell us that, okay, oh, this deflection is far higher than the other deflection. So this body is having more charge than the other one that we are comparing. So the correct option in this question, that which of the following instruments can be used to compare the magnitudes of charges on two given bodies, is the gold leaf electroscope, option C. A body of mass 2 kg is released from a point 100 meters above the ground. We are to calculate its kinetic energy 80 meters from the point of release. A good understanding of this question is going to help us to solve this. Look at the parameters that we are given. The mass of the body is 2 kilograms. Okay, it is released from a point 100 meters above the ground, but we are to calculate its kinetic energy when it is 80 meters from the point of release. Okay, so if you are to input that into a diagram, we'll have something like this. So we have 100 meters is the point of release, Okay, so the body, which is 2 kilograms, is released from that point. But what we are asked to find is the kinetic energy when it got to 80 meters from the point of release. So it's at this point that we are being asked that what is the kinetic energy at this point. This is the question that we have to solve for. Now, for us to get the value of the kinetic energy when it is 80 meters from the point of release, we make use of the principle of the conservation of energy. And here in this case, we are having energy conversion from kinetic energy to potential energy. Okay? And now for the potential energy, we need the value of the mass of the body, which we got to be 2 kilograms, then the height at which is falling from, which we got to be 80 meters, and the acceleration due to gravity, g. So that potential energy at 80 meters is going to give us mass times the acceleration due to gravity times the height. So now for the mass, we have been given as 2 kilograms. Okay, acceleration due to gravity we can take as 10 meters per second square, and then the height we have been given as 80 meters from the point of release. Okay, we don't use 100. We are asked to calculate its kinetic energy 80 meters from the point of release. So we use 80. And in this case, if you are to multiply this, 2 times 10 is 20, 20 times 80 is 1600 joules. So from the options, the correct answer is option A. Which of the following waves is not mechanical? Is it waves in pipes, water waves, radio waves, or sound waves? For us to be able to answer this question, we need to understand the two basic types of waves that we have. And in physics, we have categorized them as mechanical and electromagnetic waves. The distinctive features of mechanical waves is that they need material medium for them to be propagated, for them to move from one point to another. And they are produced by the oscillation in a material medium. So if you are looking at mechanical waves, we'll be talking about waves in pipes, because that is needing the pipe to propagate from one point to the other. Water waves, because the water is the medium of propagation of those kind of waves. And sound waves, because air is the medium through which that type of wave is propagating. Now, looking at radio waves are not mechanical because they don't need any material medium for their propagation. They can even travel in a vacuum, and they consist of disturbances in the form of varying electric and magnetic fields. So that's why you need a radio antenna to broadcast them and to also receive them. So out of all these options, the wave that is not a mechanical wave is radio wave. So option C, radio waves, is the correct option. A loaded spring is set in simple harmonic motion. The force that tends to restore the load to its equilibrium position is what? Is it adhesive, elastic, frictional, or gravitational force? If you are to look at the example of what is being shown here, these are diagrams that can help us to depict that particular question as it's being asked. And we are being told that it is set in simple harmonic motion, meaning that looking at this is the loaded spring. Okay, this is a spring, this is a spring, these are springs. Okay, and then it is loaded. It can be either loaded from the top, as in the first case A, or it can be loaded to the side, as in this second case. And now if it is set in simple harmonic motion, that means that this particular attachment will first move towards the downward position and then also move back. And for this case, that means it will first move to the right if it is displaced to the right, and also move back to the left. Then it will continue the to and fro movement, constituting a simple harmonic motion. Now, we are being asked that what force is tending to restore the load to its equilibrium position. That means to its starting position. Like here, this can be the starting position. So if it moves here to the right, it will still go back to the starting position before moving back to the left. And the same also in this case, maybe here, that will be the original position. Okay. Now, If you look at the options that we are given adhesive, elastic, frictional, and gravitation. Frictional force is a force that tends to oppose motion. Gravitational force is a force that acts as a reason of the Earth's gravitational field pulling body towards the center of the Earth. Adhesive force is a force that mostly occurs in molecules to adhere them together, to bind the energy together. So in this particular case, the only option that is correct is the option B. It is the elastic force, because the spring is actually having some elastic properties that is tending to restore the load back to its equilibrium position. So the correct answer is option B. It is the elastic force. Which of the following cases cannot produce total internal reflection? A light ray traveling from A, glass to water, kerosene to air, air to water, water to ice. Before we can solve this question, we need to understand total internal reflection before we can find the case which cannot produce the total internal reflection. And as a reason of guide, I've drawn up this. For total internal reflection to occur, there are two conditions that need to be met, and these two conditions are highlighted as shown on the board now. The first one here is that light must be traveling from a dense medium to a less dense medium, meaning that the source of the light, the point where the light is emanating from, will be a denser medium. It should be the medium in which it is difficult for air to really pass through compared to the other medium. So like in this diagram, this region that is indicated in light blue will be the dense medium. So this is the dense medium. Okay. And then the outer one is the less dense medium. That's the first condition that needs to be met. And then the second condition, the angle of incidence must be greater than the critical angle. The critical angle is the point at which the rays of light is at normal to the surface where the reflection is occurring. So it is theta C, is this theta C in this particular diagram. So that is the critical angle. And you can see immediately after that angle is exceeded, here in this case here, we now have total internal reflection occurring. So let's look at the options we are given. Definitely the options are not talking about the angle of incidence being greater than the critical angle, meaning that we need to look at the density of the medium that the light is traveling from and that the light is going to. So in the first case, we have that glass to water. Definitely glass is denser than water. Okay, so glass is a dense medium, water is a less dense medium. So total internal reflection can occur in that medium. In the second option, kerosene to air. Kerosene is a dense medium while air is less dense. If we are looking at the density of the medium, we need to consider something like, let's say, the heaviness of the medium. Okay, so the dense one will not permit light rays to really pass through because it is dense, whereas the less dense will permit light rays to pass through because, of course, it has some permeability. The light can easily pass through it better than the dense medium. So looking at kerosene and air, kerosene will be dense, the air will be less dense. Okay, now looking at air to water, air and water, air is less dense compared to water, so the light ray, we find it easier to propagate through the air than through the water. So definitely this option C is a point in which total internal reflection cannot take place. The other one is water to ice. Water and ice, maybe you may not be too sure, but definitely air to water, that is a critical case. So for this question, which of the following cases cannot produce total internal reflection? It is definitely option C. Air to water cannot produce total internal reflection because it has to go from a dense medium to a less dense medium. And so C is the correct answer. The vacuum in a thermal flask reduces heat loss resulting from, is it radiation only, or conduction and convection only, or radiation and convection only, or conduction only? To understand this, let's have a look at the thermal flask. And here we are seeing the thermal flask with a stopper at the top, a double walled container, then the containing liquid which we need to keep hot or cold as the case may be, insulated support, silver sulfur double glass top, and the vacuum. Okay, so now our question is asking us that from all this, what is the work of the vacuum? Okay, and if you look at the diagram, this is the vacuum, and we are to determine the kind of heat loss that the vacuum is preventing in the thermoflask. Now, looking at this diagram and by understanding of the transfer of heat, looking at the first option here, radiation only, the vacuum cannot be what is responsible for reducing the heat loss by radiation, because radiation is the heat loss that occur without any material medium. Okay, so actually the radiation loss can occur whenever there is vacuum. So definitely the vacuum is not stopping the heat loss from radiation. Now, looking at the second option, conduction and convection only. Now, what is conduction? Conduction is a heat loss that occurs as a reason of heat loss through a solid body from a region of higher temperature to a region of lower temperature. And now, looking at vacuum, vacuum will not allow conduction loss because it's a vacuum. So for conduction to occur, it needs a solid medium. Okay, so definitely the vacuum will stop that kind of heat loss. Looking at convection, convection is a heat loss that is associated with liquid or gas. Okay, so of course the vacuum is an empty space, so there's no liquid, there's no gas. So definitely what the vacuum will reduce in the thermoflask is heat loss by conduction and convection. So the correct option here is option B, by conduction and convection only. The diagram above represents an experimental setup for verifying which of the following laws. We have the Lenz law, refraction laws, reflection laws, and mirror formula. Let's look at the diagram to determine which law this is being set up for. So looking at the diagram that have been given, we can deduce that this O here is the object and this I is the image. Okay, so we have an object and image. We have this line as solid and we have this line as a broken line. What we can notice is that look at this distance to this distance, they are approximately the same, and that is telling us something like the object distance is equal to the image distance. Okay, that's the first observation that I'm noticing. And then if you look at this point, let me call that point A, let me call this point B. At point A, look at this angle and look at this angle. This is definitely the incidence ray. So I can say at point A, I can see that the angle of incidence in the first case is the same as the angle of reflection, okay, for the first case. And also at B, I can also notice that, look at this also at B, this angle and this angle, okay, this I2 and R2, I can also observe that they are the same. So I can also see that I2 is equal to R2. So the angle of incidence and the angle of the reflected ray are both equal. So I have this observation that I can deduce from the diagram that I'm giving. The object distance is the same as the image distance. At every point in which we draw rays of light, the angle of the incidence ray is equal to the angle of the reflected ray. These are properties of the mirror. The mirror is a case in which there is this wonderful symmetry all across the image of the object that is being formed, that we have the object distance and the image distance, they are equal. The angle of incidence and the angle of reflection, they are also equal. And so the solution to this problem is definitely option D. So this is the mirror formula, and the correct option is option D. Which of the following statements about a moving object is correct? So we are given these four options that we will do well to examine one after the other. And so if we consider a moving object, let's say this object is moving in this direction. Okay, so in the first case, we are told that when accelerating, the resultant force acting on it must be equal to 0. From the equation for force, we know that force is mass times acceleration. Okay, so for this statement that is saying that the resultant force F must be equal to 0, that is not going to be possible, because when the acceleration A is 0, definitely F will also be equal to 0. So option A is not going to be the correct statement. In the second case, we are being told that there must always be a non-zero resultant force acting on it. But the fact that a non-zero resultant force is acting on it does not mean that the object may be moving. For example, we can have the Earth's pull on it due to the acceleration due to gravity, but that does not mean that the body is moving. Okay, then we can knock out option B. Option C, at a steady velocity, the resultant force acting on it must be equal to 0. What does a steady velocity imply? A steady velocity means that the change in velocity is 0. So we can say V, the final velocity minus initial velocity, is 0. This warrants that, of course, since it's a steady velocity, acceleration, which is the change in velocity over t, is also equal to 0. So therefore, this acceleration will be 0 and the force will also be 0. Definitely that is going to be true, because at steady velocity, the resultant force acting on it must be equal to 0. There is no force to warrant the increase in acceleration. So option C is looking like our likely answer. But let's look at option D. At the steady velocity, the air resistance must be equal to 0. No, the air resistance has nothing to do with the steady velocity. So definitely the correct option out of all these four is option C, that at a steady velocity, the resultant force acting on it must be equal to 0. If the efficiency of a transformer is 100%, which of the following equations would be correct? If you are to consider the ideal transformer, especially the equivalent circuit, and we are to look at the parameters that we have, ideally what is given is that the voltage across the primary coil is proportional to the number of turns in the primary segment of the transformer, and the same is also applying to the secondary segment of the transformer. So if we are to look at the primary segment, okay, the primary, we can say that the voltage Vp is very proportional to the number of turns Np, and also in the same way, looking at the secondary side of the transformer, we can say the secondary voltage is proportional to the number of turns of the coil of the secondary side of the transformer. Now, if you are to include the proportionality constant, we can just divide these two statements so that we have Vp over Vs is equal to Np over Ns. Okay, such that we can conclude that Vp Ns is equal to Vs Np. Now we need to look at our equations, the options that we are given, and see which is corresponding to this. In the first case, we are having NPEP is NSES. There is no, look at what we got here. There is the primary multiplied by the secondary multiplied by the primary. But in option A, that is not what we are having. So definitely option A cannot be the solution. Okay. Then in the option B, the NSIP is equal to the NPIS. Okay. Looking at that, we are having a crossover, the number of turns in the secondary and the current in the primary. Okay. Then the number of turns in the primary and the current in the secondary. Now, the current is actually produced as a result of the voltage. So this our equation, we can also say this is synonymous to the current in the primary multiplied by the number of turns in the secondary is equal to the current in the secondary multiplied by the number of turns in the primary, which is confirming that option B is a likely solution. Let's look at the other options. The number of turns of the secondary and the current of the secondary is equal to those of the primary. That is wrong because we are having a cross equation. Now looking at this, number of the currents in the primary and the induced EMF in the secondary. No, it's not the relation between the current and the induced EMF. It is the turns ratio that we are using, so we need to make use of the number of turns. So definitely the correct option among all these that we are given is option B. NSIP is equal to NPIS. A freshly demagnetized bar magnet is placed in the east-west direction to ensure that what is the purpose of that placement on the freshly demagnetized bar magnet. To understand this, let's look at a means of demagnetizing a bar magnet as shown on the diagram. Now, here we are using the process of hammering. It can be any of the other processes. What this process is doing ideally is to break the alignment of the magnetic field lines on the magnet such that instead of the magnetic field to be flowing as shown, we are going to have breakage and the alignment is going to be lost. Okay, so this is what is happening, is breaking that alignment, and once that alignment is broken, for the magnet not to realign, it is placed in the east-west direction so that the north-south pole will not realign what we are just scattering from the magnet. So the correct option out of all the options that we are given is that the molecular magnet will remain randomly arranged. They will be random. It won't be aligning in the way that it is for the magnet when it was not demagnetized. So the correct option here is option A. Which of the following graphs of a charge Q against potential difference V across capacitor is correct? So we have all these four graphs and we are trying to see which of these graphs is correct to express the relationship between the charge Q and the potential difference V across a capacitor. If we are to look at the capacitor with two dielectric plates, one plate and another plate, okay, separated like that. Ideally, there is a voltage that is going through the capacitor, voltage V, let's say is capacitor to capacitance C, okay. Then there is a charge associated with the capacitor Q. The relationship between Q, the charge of the capacitor, and the voltage V is given as Q is equal to CV, where Q is the charge, C is the capacitance of the capacitor, and V is the voltage. Now, if we recollect the equation of a straight line, the equation of a straight line says that Y is equal to mx plus C. And we have to compare this equation of a straight line to the equation Q is equal to CV. We can see that this is the same as CV plus 0 because the intercept C is now amounting to 0. Okay, the variable x is now amounting to voltage V, and the slope m is amounting to the capacitance of the capacitor, and then our y will now be synonymous to Q. If we look at this critically, we can see that an increase in voltage will result to an increase in the charge Q across the capacitor. So this is a classical example of a straight line graph that is starting from the origin, since the intercept C is 0. So out of all the options that we are given, the one that is correct is option B. Option B is expressing correctly the equation between the charge Q and the potential difference V. You see, this is Q and this potential difference V of the capacitor. So correct option is option B. A small amount of air is introduced into the vacuum above the mercury in a mercury barometer tube. The mercury level goes down because the air molecules, we are given 4 options to consider. Is it because the air molecules eat the mercury and make it to expand? Or is it because the air molecules increase the pressure above the mercury? Is it because the air molecules cool the mercury and make it to contract? Or is it because the air molecules decrease the pressure above the mercury? For us to understand this, let's have a look at the mercury barometer tube, and it is as shown on the board now. So what we are being told is that there is a small amount of air that is introduced into the vacuum. So this is the vacuum, this is the vacuum. So now, if you are to introduce a small amount of air, let's put that in blue, okay? So let's say this is small amount of air. What we notice that will happen is that this air that is introduced will exert some pressure on the mercury, and that will drop the level of the mercury. So the correct option in all the options that we are given is that the mercury level, this mercury level will have to go down, okay? It will have to go down, it will go down because the air molecules will increase the pressure above the mercury. So the correct option in this case is option B. It will increase the pressure above the mercury. In this question, we are to calculate the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. We are given the specific latent heat of fusion of ice to be 3.36 times 10 raised to the power 5 joules per kilogram, and the specific capacity of water to be 4.2 times 10 raised to the power 3 joules per kilogram per Kelvin. Okay, now if you are to look at this question, there are two phases that we need to focus on to get the amount of heat needed to change the temperature of the ice at 0 degrees Celsius to 80 degrees Celsius, and it is as shown on the board. First, the ice at 0 degrees Celsius, okay, like here is at 0 degrees Celsius. We first need to transition to water also at the same temperature. The amount of heat that will be applied to this system, we first need to convert the ice at 0 degrees Celsius to water at 0 degrees Celsius. And then for the water that is now obtained, the heat will be added to the water to transition it from 0 degrees Celsius to 80 degrees Celsius as required in the question. So these are the two stages that we need to focus on. But first, we notice that the mass of the ice was given in grams. So that mass we need to convert to kilogram, so that we know that that mass will be 60 over 1000 kilograms. Okay, and that will be, and divide this, that will be 0.06 kilograms. That's the mass of the ice, and of course subsequently the mass of the water that we'll be working with. So now the two stages that I was referring to that we need is that first we need the amount of heat that will convert the ice at 0 degrees Celsius to water at 0 degrees Celsius, and that will be given as the mass of the ice multiplied by the specific latent heat of fusion of ice, which was given as 3.36 times 10 raised to the power 5, okay, because that will be the amount of heat that we need to convert that ice to water, even though the temperature is not changing. But that's not all. We also need to compute the amount of heat needed to convert the water from 0 degrees Celsius to 80 degrees Celsius, and for that we need to use the mass multiplied by the specific capacity of water multiplied by the change in temperature. Okay, so these are the two steps that we need to go through to get the amount of heat that will be needed in this system. And looking at the parameters that we are given, we already have our mass in kilogram. We are given the specific latent heat of fusion of ice, and we are given the specific capacity of water, and we can also see that we can get the change in temperature. So now with the parameters that we are given, we can look at how to evaluate this. So the heat that is needed as requested in the question will be first the mass at 0.06 kilogram multiplied by the specific latent heat of fusion of ice, that's 3.36 times 10 raised to the power 5 joules per kilogram, okay, plus now for the amount of heat needed to raise the water from 0 degrees Celsius to 80 degrees Celsius. We still have the same mass because it's still the ice that was converted to water. So we still have 0.06 kilogram times the specific capacity of water, which is 4.2 times 10 raised to the power 3 joules per kilogram per Kelvin, multiplied by the change in temperature. Now, we don't need to be confused. The change in temperature in Celsius is the same as the change in temperature in Kelvin. Okay, so because of the consistency of the units, I'm going to put that in Kelvin because it's a linear change. If you have a 10 unit change in Celsius, it's also the same 10 unit change in Kelvin. So my change in temperature is 80 minus 0 because we are starting from 0 and going to 80. So the difference is 80 minus 0, and that is 80. So 80 multiplied by 80 Kelvin. So this is the value this is the amount of heat that we need to compute to get the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. So to compute that, I will bring in my calculator, and first I have 0.06 times 3.36 exponent 5, okay, plus the second case 0.06 times 4.2 exponent 3, all right, times 80. Okay, then I need to check, do I get all my values correct? I hope I didn't make any mistake. And once that is done, I can press the equal to sign, and so I have 40,320 joules. So this is going to give me, so the amount of heat needed is 40,320 joules. And of course, looking at the options, we are given kilojoules. So kilojoules is meaning that in thousands, so that will warrant 40.32 kilojoules as a solution to this, and that is option C. The correct option to this question is C, 40.32 kilojoules. The wire of a platinum resistant thermometer has a resistance of 3.5 ohms at 0 degrees Celsius and 10.5 ohms at 100 degrees Celsius. So we have to calculate the temperature of the wire when its resistance is 7.5 ohms. To address this question, I would love to drop a scale. Let's call it a linear scale. So if I want to just drop something like this, and we have the lower scale and the upper scale, we're told that the thermometer has a resistance of 3.5 ohms at 0 degrees Celsius. So let's say this is 0 degrees Celsius at the minimum, okay, that is corresponding to 3.5 ohms, and then it's having a resistance of 10.5 ohms at 100 degrees Celsius. So at the maximum, this is 10.5 ohms, and we're having this as 100 degrees Celsius. So we have to find the temperature of the wire when its resistance is 7.5 ohms. So when the resistance is, like, say around there, this is 7.5 ohms, but we don't know the temperature of the wire. So let's call that X. Let's say this is X degrees Celsius. I know students generally would love to bring in a formula to try and use, but I would rather want to approach this from the bottom up. Okay, let's say we are just starting from scratch and trying to solve this as a relational scale so that we can find the value of X. Since this is a linear scale, one of the things that can be done is to say that we can take some reference points, and already we have our reference point as the base, 0 degrees Celsius and 3.5 ohms, and then we can interpolate the value of X that is corresponding to 7.5 ohms that we are trying to find. And this is how we are going to do that. We can say that x minus 0, the difference between x and the base, okay, x minus 0 over the difference between the maximum and the minimum over 100 minus 0, okay, is equal to, here, the same way we did for the temperature, we're also going to do for the resistance. So the middle case, we are saying 7.5 minus the least 3.5, okay, and we are dividing by the difference between the maximum and the minimum, that is 10.5 minus 3.5. So you can see, and this is the place location for x, which is corresponding to 7.5. This is the minimum corresponding to 3.5. This is the maximum corresponding to 10.5. This is the minimum corresponding to 3.5. So if you know this approach, you can use this method to actually solve the question no matter the type of question that is coming, not only in this type of question in which you are relating temperature to resistance. It can come in any format, but once you understand this, you can easily apply them so that you can get the solution on the fly. So if you want to solve this, you know x minus 0 is x over 100 is equal to 7.5 minus 3.5, that is 4, okay. 10.5 minus 3.5, that is 7. So if you just cross multiply, if you are to cross multiply this, we are going to have 7x is equal to 4 times 100, meaning that x will be 400 over 7. And to do that, we can just bring in our calculator and say we want to put in 400 divided by 7, and I press SD button. So this is 57.14, I can say 0.14. So I have this as S is equal to, so I can say S is 57.14 degree Celsius. But looking at our answers, we're only giving whole numbers, so we can round this off to 57 degree Celsius. And looking at the options that we are given, that means the correct option is option D, 57 degrees Celsius. A transverse pulse of frequency 9 Hz travels 4.5 meters in 0.6 seconds. We have to calculate the wavelength of the pulse. We'll be able to solve this question if we are able to relate the equation for velocity, okay, both on the frequency and wavelength and the distance and time. So we know that generally velocity is given as distance over time, okay, but looking at what we are being given here, we are given a transverse pulse of frequency 9 Hz. We also know that in that case, velocity will also amount to the frequency multiplied by the wavelength, okay. Frequency is f, the wavelength is lambda. So we just take these two formula A and we'll try and relate them together. We should be able to find this question as we are given. Now we are given from the question that there is a distance that was traveled, that the distance traveled is equal to 4.5 meters, and the time taken to take that travel is 0.6 seconds. We are given frequency as 9 Hz, and we have to find the wavelength. Lambda is what is unknown in this case. So all we just need to do is to input the value for all this into these two equations, and once we do that, our solution will come out straight and direct. So this is what we are going to do. The distance is 4.5 meters and the time is 0.6 seconds, okay. So you have to say, even say this 4.5 meters, 0.6 seconds, that is equals to the frequency is 9 Hz, and if you recollect, Hz is 1 over seconds, okay. So 9 hertz multiplied by the lambda that we are looking for, multiplied by lambda. And with this, we can just see that our lambda will be, by cross multiplying, 4.5 meters over 0.6 seconds times 9 hertz. Like I said, hertz is 1 over second, so the seconds here and the hertz will cancel out so that we can get our lambda by computing this on the calculator to say 4.5 divided by the product of 0.6 and, no, I didn't get that right, 0.6 and 9. Okay, 4.5 divided by the product of 0.6 and 9. If I press my equal to, that's 5 over 6 or 0.83. So this is equal to 0.83 meters. Okay, and looking at the option, the correct option is option C, 0.83 meters. In which of the following media is speed of sound the least? Is it air, brass, water, or wood? We need to look at this question critically to see what we are being asked. We are told that which of the following media is speed of sound is least, and they even embode that particularly. So we need to understand what we are doing when we are trying to address this question. Easily we could have said maybe it is air or wood, but let's look at the properties of the speed of sound in different medium. Now it has been established that sound travel faster in solids than they do in gas. Okay, in short, the speed of sound, if you have to look at it, speed of sound is greater in solids. In solid is greater than liquid, which is in turn greater than gases. And why is this so? This is because in solids, the molecules are more compacted together. They are packed closer together. So they are able to transfer the sound energy from one molecule to another easier than in liquid, and of course least in gases. By reason of understanding of gases, the molecules of gases are loose. They are able to move around freely. They are not packed together. So the exchange of the sound energy is not as coherent in gases as compared to solids. So looking at this question, we will see that sound will travel fastest in brass, okay, then in wood, then in water, which happen to be liquid, and just travel least in air. So the solution to this is that out of all these media, the speed of sound will be least in air. So the correct option is option A. That is where it will be least. It will be fastest in brass, but least in air. Which of the following characteristics of waves can a ripple tank be used to demonstrate? So we are giving those characteristics: reflection, refraction, and diffraction. So is it that the ripple tank will be able to, can be used to demonstrate the 3 properties of waves? That's option A. Is it only 2 and 3? Is it only 1 and 3? Is it only 1 and 2? Now we need to understand the ripple tank and its operation for us to be able to answer this question. And here is a picture of the ripple tank that I just drew and came up with. If you are to look critically, let's take them one after the other. But first, to understand the setup of the ripple tank, here, this is a shallow tank of water, okay, that can be used to demonstrate the properties of waves. And this is an oscillating paddle. This is an oscillating paddle, and that oscillating paddle can be set in motion by a motor that is mounted on it to generate ripples on the shallow tank of water. There is a viewing screen that is set up below the shallow tank to observe what is going on, and then there is a source of light suspended above the setup to provide rays of light into the experimental setup. So looking at reflection, if you are to look at reflection, now the source of light coming from the illumination, we can see that we can have rays of light coming from here and coming on the shallow tank of water, but that ray of light can be reflected, and an observer can just be looking, and that observer will see the same reflection on the screen below. So definitely reflection can be observed on the ripple tank. Okay, what about refraction? If you are to get another ray of light into the ripple tank, since this ray of light is traveling from a less dense region to a denser medium, because here above, before it gets to the shallow tank, above is here, and that is less dense. But getting to the tank, that will be a denser medium. The light ray will be refracted. Okay, so it will change direction a bit. You can have something like this. Okay, and then the observer can also see that a normal can be constructed like that, and we can get the angle of incidence, we can get the angle of refraction, and on like that. That means that refraction can also be observed. Okay, what about diffraction? An aperture can be set up on the ripple tank just as is being shown, okay, so that the ripples that are generated on the shallow tank, once it gets to this aperture, it can actually be observed to be doing diffraction just as in. So looking at all this, the correct option in this case is option A, that is telling us that the ripple tank can be used to demonstrate reflection, refraction, and diffraction. So the correct option is A, all of the above. Which of the following graphs gives the correct relationship between energy and mass when mass is converted to energy? So we are given these 4 graphs, and we are to pick the correct one that is depicting the true relationship between energy and mass when mass is converted to energy. The underlying principle of which this question is being asked is the Einstein's equation that relates energy to mass by saying E is equal to mc squared, where E is the energy, okay, E is the energy, m is mass, and c is speed of light. Okay, so this is the equation. All right, so what we need to now look is, looking at this formula, how do we translate the relationship between the energy and the mass and pick the correct option out of 4 that we are given? Definitely in the first equation, in the option A, it's telling us that energy remains constant even if the mass is increasing. But looking at the equation that we have, this cannot be the solution. So option A is definitely out of it. I want us to look at option D. Looking at option D, option D is telling us that with increase in mass, as mass is increasing, energy is decreasing. Okay, starting from the origin, and we also know from this equation that's not correct. So option D is also not it. Now considering option C, option C is telling us that there is a quadratic increase in energy as a result of increase in mass, because if you recollect your quadratic equation in which we have the x and y axis, this is actually a quadratic equation. So that is why this is going in a U shape, and this is meaning that the variable on the horizontal axis is actually of degree 2. That's why this is coming into place. That would have been correct if we have the speed of light here and no mass. But looking at what we are given, we are not looking at the relationship between energy and the speed of light. What we are looking for is the relationship between energy and mass. So that leaves us with only option B. And option B is telling us that there is a direct variation relationship between energy and mass, that an increase in mass will result to a corresponding increase in energy. And looking at this equation, E is equal to mc squared, you can see when we increase the amount of mass, okay, that will also result in the amount of the energy that will be generated. And that means the correct option out of all that we are given is option B. There is this linear relationship between them, that an increase in mass will result to an increase in energy. So the correct option is option B. An 800 kilogram car moving at 80 kilometers per hour collides with a 1200 kilogram car moving at 40 kilometers per hour in the same direction. So we need to note that these two cars, we are told they are moving in the same direction. If the cars stick together, we have to calculate their common velocity. So what we need to make use of here is the principle of the conservation of momentum, that the sum of the momentum before collision is equal to the sum of the momentum after collision. And to do that, we can look at the case scenario of the collision of these two cars, okay, as being shown on the board now. So we have, in the first case, the mass of the first car was given as 800 kilogram. You can say this is M1 is 800 kilograms and is moving at 80 kilometers per hour. So U1, the initial velocity for this particular car, is 80 kilometers per hour. Okay, we are told that if we take this as the direction in which it's moving, it's colliding with another car whose mass is 1200 kilograms. So we can say the mass of the second car is 1200 kilograms. Okay, and then this car is moving with an initial velocity of 40 kilometers per hour. 40 kilometers per hour. But they are both moving in the same direction, so you can also denote its direction as this. Now we are told that after the collision they stick together, and that's why you can see they are sticking together here. We have to calculate their common velocity. If we call that common velocity V, because these two vehicles cannot be moving to the positive direction, and this one will now be resulting into this. This will be very, very wrong. Okay, so the direction of their final velocity will have to correspond to where they are coming from initially. So this is the correct location. But then the masses for the two vehicles will now amount to the addition of M1 plus M2. So here I can say this is M1 plus M2. That's their mass. That's the sum of their masses after collision. And that is 800 plus 1002 will give me 2000 kilograms. Okay, so if I'm to use the principle of the conservation of momentum, and momentum is the product of the mass and the velocity, conservation of momentum warrants that the sum of the momentum before and after collision, they are the same. So we have the sum of M multiplied by U before is equal to the sum of M and the velocity after the collision. So that's what we need to just bring in into this equation to solve for it. And if you want to do that, that means that we will have M1 multiplied by U1, okay, plus M2 multiplied by U2 is equal to, now after the collision we are told that they stick together, so that's why we are adding their momentum, their masses together. So we have M1 plus M2 multiplied by the common velocity they are moving with V. Okay, so in that case, if we make V the subject of the formula, therefore the common velocity V will be M1 U1 plus M2 U2 over M1 plus M2. So what we need to do is, into this equation we are to input the value of all these, the mass and the initial velocity for both vehicles, and then we can solve for the common velocity. The first mass is 800, so we have 800 times the velocity is 80 kilometers per hour, okay, plus the second mass is 1200 multiplied by that initial velocity 40 kilometers per hour. When we are dividing this by the sum of the masses, m1 plus m2. m1 plus m2 we have gotten to be 2000. Okay, so all divided by 2000 kilograms. Now to evaluate this, you can just bring in our calculator and we can say, okay, first we have 800 times 80 plus 1200 times 40. Okay, I can check to see that I get everything correctly and can press equal to. So this is 112,000. Okay, so I can say that this is my V is 112,000 over 2000. So I can cut with all these 0. 2 in 11, that is 5, remaining 1. 2 in 12, that is 6. So 56 kilometers per hour happens to be the common velocity with which the two cars will move when they stick together after the collision. So you can see, to avoid the common errors that come with calculations, you can see how I first evaluated my formula and expressed them in terms of the mass and the initial velocity, and then I input my values for the mass and the velocities. This is a good way to work so that you don't make mistake in trying to move and resolve your equations. So for this question, the correct solution is option D, 56 km per hour. The mass of a load is doubled while the force acting on it is halved. The resulting acceleration of the load is what? Is it quadrupled, quartered, halved, or doubled? Let's look at the scenario that is being created here. So we can say in the first case, we have our M1, and in the second case, we are told that the mass is doubled. That's why we are showing that the mass is actually double of M1. But let's say this is M2, noting that the M2 is equal to 2 times M1. That's the implication of the fact that it is doubled. If you are to look at the force that's being applied, let's say on the M1, we have a force F1 that's being applied, and on the second case, we have a force F2 that's being applied on that body, on that mass. We are told that F2 is equal to half of A1 because they say the force acting on it is halved. Okay, so for us to put that into consideration, we can say F2 is equal to half of F1. So now we are being asked to evaluate the effect on the acceleration of the load. So what we are going to do is this. From our understanding of physics, we know that F is equal to ma, force is mass times acceleration. So in this first case, we can say that F1 is equal to m1 multiplied by a1. So 111 for the first case, and therefore our acceleration in the first case is F1 over m1. All right. Now in the second case, we can also do the same thing. We can say that from the fact that force is mass times acceleration, we're only considering this second case. Acceleration a2 will be f2 over m2, right? But looking at what we have deduced initially, that m2 is 2m1 and f2 is half f1, we can input that into this equation to say this is the same as, what is our f2 is 1 over 2 f1, okay? And what is our m2? m2 is 2 m1. Now this is what we need to evaluate to say that we can see that our a2 is going to give us, this is as if we are saying 1 over 2 f1 divided by 2 m1, and by reason of operation of mathematics, you know, that will give us 1 over 2 f1 times 1 over 2 m1. So this will be 2 times 2 is 4. We have 1 over 4 f1 over m1. Now look at this. What's f1 over m1 here? That is a1, meaning that what we have is that the a2 is equal to 1 over 4 a1. Okay, that is the resolution of the second acceleration that we deduce from our workings, and that means that that acceleration had been quartered. 1/4 is a quarter. So the correct option out of all these options will be option B. The resulting acceleration of the load is quartered whenever we double the mass and we halve the force. So option B is the correct answer. In this question, we are asked what the maximum and minimum thermometer reads. Is it the maximum temperature during the day and the minimum temperature at night at all times? Or the maximum temperature at night and minimum temperature during the day from the last reset? Or the maximum temperature at night and minimum temperature during the day at all times? Or the maximum temperature during the day and the minimum temperature at night from the last reset? For us to be able to answer this question, we need to understand the operation of the maximum and minimum thermometer, and it is as shown on the board below, in which there is a flow of mercury below and it is granulated in 2 units. There is a Faraday unit in the inner region and the Celsius unit on the other region. The maximum is taken from the bulb to the right and the minimum reading from the bulb to the left. That bulb is containing alcohol plus low pressure gas, and to reset, the marker is normally moved to the upper region, and that will be the reset, and it is from that reset that the temperature will be taken. So looking at all the options that we are given, the correct option will have to be the option D. So the maximum and minimum thermometer reads the maximum temperature during the day. Of course, the day will be hotter, and minimum temperature at night. Of course, the night will be cooler, but it is based on the last reset. That is the key word that we need to take. It's not at all times, okay? It is at the last reset. So the correct option is option D. An AC generator can be converted to a DC generator by replacing is it that we replace the commutator with an armature, or replace the armature with a commutator, or replace the commutator with slip rings, or the slip rings with a commutator. There are generally 2 methods to convert an AC generator to a DC generator. The other option that is not being mentioned there is by the use of rectifying diodes. But since they are not talking about this, we need to look at the AC generator and the DC generator, and this is an overview of those two. Here, this is the AC generator, and to the left, this is the DC generator. So what is generally done is that, looking at the AC generator, you can see we have a slip ring, but instead of the slip ring, we use a commutator. Okay, so what happens is that the slip ring is replaced with a commutator, and doing that, the output, instead of we having a sinusoidal output, in this particular case, we are going to just have half wave output, because the alternating output has been changed to a direct output. So we are not having it alternating between the positive and the negative. So the correct option out of all the options that we are given is option D. We replace the slip ring with a commutator, and with doing that, we can convert an AC generator to a DC generator. Which of the following statements is the correct reason for using soft iron in making the armature of an electric bell? Is it that it's a diamagnetic material, or it loses its magnetism readily, or is not easily magnetized, or it retains its magnetism for a long time? Now, let's understand the basic principle of operation of the electric bell for us to be able to answer this question. So in looking at the operation of the electric bell, what happens in the electric circuitry? Now, once this switch is pressed, what happens is that an electric current is induced in the electromagnet here, this and this, and that electromagnet will cause that this soft iron armature, this iron armature will immediately get magnetized, and once it will become magnetic, then it will draw this spring onto it, and as a result of this hitting it, the hammer will continually hit the gong as long as the switch is being pressed. That being said, immediately the switch is released, we want this electromagnet to actually stop its induction on the soft iron armature, and immediately that stops, we want the soft iron armature to lose its magnetism. Losing its magnetism will cause the spring to stop functioning, and then there will be no sound coming into the gun. So the feature we need on the soft iron armature is that it should lose its magnetism readily. Once the switch is released, it should also lose its magnetism. And in that case, the correct option out of all the options we are given is option B, that the armature should lose its magnetism readily. So we use soft iron in making that armature. So option B is the correct answer. In this question, we are told that the diagram above illustrates a meter bridge circuit under balanced condition. We are to determine the value of X. What we need to understand is that we are talking about a meter bridge that is under balanced condition. And for a meter bridge, is ideally set up with a 1 meter rule. So meaning that from this end to the other end is 1 meter, which is the same as 100 centimeters. But already we are told that X have been taken out of it, so the remainder will be 100 minus X centimeters. So furthermore, we are now seeing that the 2 ohm resistance corresponds to X centimeters, and the 5 ohm resistance corresponds to 100 minus X centimeters. So we can just express that by saying 2 corresponds to X, okay, and then 5 corresponds to 100 minus X. What we need to do with this to solve is to just cross multiply these two equations so that we have 5x is equal to 2 times 100 minus x, and if we open the bracket to the right hand side, we have 2 times 100 is 200 minus 2 times x is 2x, so that we can take this minus 2x to the left hand side, and that will give us 5x plus 2x is equal to 200. 5x plus 2x is 7x, and that is equal to 200. To solve for x, we can divide both sides by 7. So this 7 will cancel this 7, and x will now be 200 over 7. Okay, so x is 200 over 7, and for us to express that on the calculator, we can just say 200 divided by 7. What's that going to give us? I'll press the SD button to express that answer in fractions, from fractions to decimal, and here we are seeing 28.57 centimeters. So S is 28.57 centimeters. But looking at the options, we have 71.4, 10.0, 28.6 with 7.2. We don't have 28.57, but we can see that that is a rounding up to this particular value, because what we do is that we can say that means x is approximately equal to 7 can be rounded up to 1, and that one will be added to 5, so we have it as 28.6 centimeters. So for this particular question, the correct answer is option C, 28.6 centimeters. Which of the following devices is used for storing electric charges? So we are given transformer, ammeter, potentiometer, and capacitor. Let's look at the functions of each one of them. A transformer is used to step up or step down voltages and currents. So this is a voltage or current scalar device. Okay, you either step it up or step it down. The ammeter is an instrument used to measure current. The ammeter measures current I. Okay. The potentiometer is used to measure voltage, and is actually the device that is mostly used to control electric devices, like say the volume in your audio mixer and co. However, the capacitor is a device that is used to store electric charge. So these store charges, and as such, the correct option out of all that we have been given, that which of the following devices is used for storing electric charge, the answer is capacitor, option D. An electron of mass 9.1 times 10 raised to the power minus 31 kilogram moves with a speed of 2.0 times 10 raised to the power 6 meter per second round the nucleus of an atom in a circular path of radius 6.1 times 10 raised to the power minus 11 meters. So this information has been provided for us, and we have to use it to answer questions 30 and 31. So first, in question 30, we are being asked to determine the angular speed of the electron. Let's have a look at the information that was given to us. So this is our electron. Let's say this is our nucleus. This is the nucleus at the center. Okay, this is the nucleus. So from the nucleus, we are told that the radius of the movement of the electron is given as 6.1 exponent minus 11 meters, and we're given the velocity, the speed with which the electron is moving to be 2.0 times 10 raised to the power 6 meters per second, and the electron itself is having a mass. The mass of the electron was given as 9.1 times 10 raised to the power minus 31 kilograms. So these are the information that we need to make use of to evaluate the angular speed of the electron. And to get the angular speed of the electron, the angular speed W is given as velocity over the radius, the speed with which the electron is moving over the radius of its orbit around the nucleus. So to evaluate that, we can just say W is equal to, what's the speed that we are giving? 2.0 times 10 raised to the power 6 meter per second, okay, over the radius of the orbit, which is 6.1 times 10 raised to the power minus 11 meters. But now that angular speed, the unit will be in radians. So we need to bring in our calculator to calculate this. So if I bring in my calculator, I can say 2 exponent 6 divided by 6.1 exponent minus 11. That's the ideal way to input this. And if I press my equal to, so I'm getting this as 3.27 or approximately 3.28 exponent 16. So this is equal to 3.28 times 10 raised to the power 16 radian per second. And looking at the options, we can see that option A, that is the correct option. So that is the question number 30. So here in question number 31, still with the information that we are given, we are also asked to calculate the centripetal force acting on the electron. Okay, so what is the force that is acting on the electron and binding it to the nucleus of the atom? There is also a formula that is generally employed in use when we want to find that centripetal force, and it's given as F is equal to mv square over r, and m, that's the mass of the electron, v is the speed of the electron, and r is the orbital radius of the electron to the nucleus of the atom. So we just need to evaluate that by inputting all the necessary values. The mass is 9.1 times 10 raised to the power minus 31, okay, multiplied by the square of the velocity. The velocity is 2.0 times 10 raised to the power 6, okay, but the velocity is raised to the power 2, so we have raised to the power 2 here, all divided by the radius of the orbit of the electron around the nucleus of the atom, which is given as 6.1 times 10 raised to the power minus 11. So we can evaluate that, and if we bring in our calculator, we need to put the things in the right perspective, put them into the calculator correctly. So I'm going to put the numerator in bracket. I have 9.1 exponent minus 31, okay, times, now we have 2 6.0 times 10 raised to power 6, but this is now raised to power 2. Then I can close the bracket for the numerator, the ones on top, divided by the denominator is 6.1 times 10 raised to power minus 11, and then close the bracket. And I need to confirm, I hope I didn't make any mistake, 9.1 times 10 raised to power minus 31, 2 times 10 raised to power 6 raised to power 2, okay, then 6.1 times 10 raised to power minus 11, I can press equal to, and this is giving me 5.967 times 10 raised to power minus 8, or I can say 5.97, so this is 5.97 times 10 raised to power minus 8 newtons. Looking at my options, I didn't see any option corresponding to that, but we can see here, we can see 6, and that's an approximation of what we just got. So this is approximately equal to 6.0 times 10 raised to power minus 8 newtons. So the correct answer in this particular case is also option B, 6.0 times 10 raised to power minus 8 newtons. A device consumes 100 watts of power when connected to a 120 volt source. We have to calculate its resistance. So let's say this is the voltage source and the device is a load here. Okay. So we are told that the power that it consumes is equal to 100 watts, and voltage is 120 volts. And then we have to calculate the resistance R of this device. Generally, power for an electrical device is given as P is equals to IV, but looking at this question, we know that we were not given I at all, but from Ohm's law, we know that V is equal to IR. That's a statement of Ohm's law. Since V is equal to IR, we can evaluate I to be V over R. And if we are to use this in our equation for power, then power will be I, we have gotten to be V over R, right? Which is I, that's I. Then we'll multiply that with V, meaning that power is the same as V squared over R. But looking at this question, we are looking for R. We know P and we know V. And in that case, we can just say, we can invert this equation, make out the subject of the formula so that R will be V raised to power 2 over P. And what's the value for our V? Our V was given as 120 volts. So we have 120 raised to power 2 divided by the power. The power was given as 100 watts. Right? 120 raised to power 2, if you take our calculator, 120 raised to power 2, that's equal to 14,400. So we have this as 14,400 divided by 100. So these two zeros will cancel these two zeros, so that our resistance will be 144 ohms. And if you look at our options, option D is corresponding to that the resistance for this device that consumes 100 watts of power when connected to a 120 volts source is 144 ohms. Which property of a wave remains constant when the wave travels from one medium to another? And here we are given 4 properties of a wave and we have to pick one of them. The correct option out of all these options is option D, frequency, because if you look at the wave formula, velocity is frequency times lambda. Generally, based on the medium, the velocity will be affected, the wavelength will be affected, but the frequency will not change. And a very good example of how to explain this is, consider your radio waves that, let's say there is a radio station that is broadcasting, and normally they are broadcasting at whatever frequency they are broadcasting. Wherever you are, if you tune in your device, say your radio device and you are to get their signal, one of the things you notice is that your antenna will pick the frequency of the radio station no matter what it is. So if it is, let's say it is 92.5 FM megahertz, it's not going to change. It's the same frequency with which they are broadcasting that you still receive it, but every other thing they will definitely change. So the property of a wave that remains constant when the wave travels from one medium to another is frequency. So the fact that you are here in your room, maybe this is the location for your room, or maybe you are actually even underwater, you are on the sea, and you have your phone with you, maybe you're in a submarine. Once the frequency can get there, you will still get that wave at the same frequency. The frequency will not change. So the correct option is option D. The anomalous expansion of water occurs in the range, is it 0 degrees Celsius to 100 degrees Celsius, 0 to 4 degrees Celsius, 4 to 100 degrees Celsius, or minus 4 to 0 degrees Celsius. Let's try and understand the anomalous expansion of water. This is a diagram that is showing that anomalous expansion of water. And what we notice is that, let's consider a case in which we are freezing water. Okay, from the boiling point at 100 degrees Celsius, let's say we are freezing water. Ideally, what we expect is that since the water is initially liquid, okay, as it is liquid, the more we are freezing, the liquid will begin to solidify, okay, and if it is solidified, it will become more dense. So it will become more dense, it will get more compacted together. But what is noticed with water is that once water gets to 4 degrees Celsius, what happens is that the water will begin to expand. So instead of the contraction that we were noticing before, the volume or the mass of the water will seem to expand. And of course, this is abnormal, hence the name anomalous expansion of water. So what happens during the anomalous expansion of water has just been explained, and it typically occurs between 0 to 4 degrees Celsius. So this is the range, and looking at the options for what we are given, we can see that the correct option out of all those options is option B. It occurs in the range 0 degrees Celsius to 4 degrees Celsius. A ray of light traveling from a rectangular glass block of refractive index 1.5 into air strikes the block at an angle of incidence of 30 degrees. We are to calculate its angle of refraction. Okay, so this will warrant that we are going to be using Snell's law to calculate the angle of refraction given the angle of incidence. And if we are to draw the diagram of the information we are given, so let's say this is our rectangular glass block. Okay, so this is the glass, and let's say here we have the here, this is the here. So what we need to look at in trying to solve for this is that in this question we are told that the light ray is traveling from, look at that word, we are told that it is from a rectangular glass block. So if you want to depict that correctly, we could have said that this is the ray of light. Let me use blue would be ideal. This is a ray of light traveling and getting to the edge of the glass block, and at the point where it's getting to the edge of the glass block, we can draw a normal. So this is the line of the normal, but the ray of light will now be refracted. So to be refracted from here, and all these angles are measured relative to the normal. So I can say the ray of light is traveling from the glass block and then to here, and then the angle of incidence is 30 degrees. So this is 30 degrees, and what we are asked to find is the angle of refraction. This angle, we can call it angle theta. Okay, so okay, let's use the ideal. If this is I, this is R in that particular case. So looking at this, Snell's law is the formula that is employed to solve this type of question, and it's saying that the refractive index is the sine of the incident angle to the sine of the refracted angle. Now we are giving n as 1.5, we are giving the angle of incidence as 30, and then we are looking for the angle of refraction. So all we need to just do is to plug in those values, that n, which is 1.5, is equal to the sine of the incidence angle sine 30 over the sine of the refracted angle sine r. Okay, this is like over 1, and if we are to cross multiply, you can see that sine r, which is sine r, is equal to sine 30, which is 0.5 over 1.5. 0.5 divided by 1.5, let's evaluate that. 0.5 divided by 1.5, that's 0.333. okay, so it's 0.333, and it will continue like that. That's why the calculator just put a bar on top, that is a continual loop. Okay, but we want to find r, we need to evaluate the arc sine of this. So r will be the arc sine of 0.333 and on like that, and you can just evaluate that on the calculator. Shift sine will be the arc sine. Is our answer. We want to find the arc sine also, and we just press answer and close the bracket. So that is going to be 19.47. that is 19.47 degree. And looking at the options, we didn't have 19.47, but we have 19.5, meaning that the approximation was done, 7 was converted, was rounded up and added to 4, making it 19.5. So the correct option out of this question is option B, 19.5 degrees. A rectangular piece of iron measuring 4 centimeters by 3 centimeters at 20 degrees Celsius is heated until its temperature increases by 100 degrees Celsius. We have to calculate the new area of the metal, but we are given the linear expansivity of iron as 1.2 times 10 raised to the power minus 5 per Kelvin. So, looking at this question, I've been seeing a whole lot of terrible solutions that are proposed, but we're going to find out how to tackle this question so that even if we meet it in subsequent papers, we'll know the proficient and the correct way on how to handle this question. So let's look at the parameters we are given. We are given the linear expansivity of iron. So we have the linear expansivity of iron is 1.2 times 10 raised to the power minus 5 per Kelvin. We are given the dimensions of the piece of iron as 4 centimeters by 3 centimeters. So with that, we can calculate the area of the piece of iron. We know area is length times breadth, so that's 4 centimeters times 3 centimeters, which is 12 centimeters square. Okay, then we need not to be confused. We are given the initial temperature as 20 degrees Celsius, but we are told that there is a temperature increase by 100 degrees Celsius. So 20 degrees Celsius is not going to be our concern because we have been given the temperature increase already. So if we want to put that in the right perspective, our change in temperature is 100. Okay, that is the correct thing. It's not that we are saying 100 minus 20. If you have to use that, we'll definitely miss this particular question. But now, looking at this question, we are told that we have to find the new area of the metal when it has changed its temperature by 100 degrees Celsius. So definitely that means this is A1. This is A1 that we just computed as 12 centimeters square. But we are looking for A2. So we have to find A2. That's what the question is giving. But look at this question. We are giving the linear This is where students will get to miss this question. We are given the linear expansivity of ion, not the area expansivity of ion. So for us to get the area expansivity of ion, when given the linear expansivity of ion, what we use is the area expansivity of ion is equal to 2 times the linear expansivity of ion. This is going to really help us to solve our question, and if we just miss this out, definitely we are going to miss out on the solution to this question. So this is the correct approach to take, that the area expansivity of ion is 2 times the linear expansivity of ion. Therefore, the area expansivity of ion is going to be 2 times 1.2 times 10 raised to the power minus 5 per Kelvin, and that is going to give us 2 times 1.2 is 2.4 times 10 raised to the power minus 5 per Kelvin. Okay, so that is the first of what we need to understand. Then, originally, if you are to use the formula for the area expansivity of ion, that is given as change in area A2 minus A1. Initial area is A1, the final area is A2, divided by the original area multiplied by the change in temperature. So looking at all these parameters already, we know our area expansivity, we know the change in temperature, we know the original area A1. All we need to now do is just to compute A2. So if you are to solve for that, I like expressing my equations linearly before trying to solve with the calculator. So here, if I cross multiply, I can say beta A1 theta is equal to A2 minus A1, and if I move A1 to the left hand side and rearrange, I can say the final area will be A1 plus beta A1 theta. And if we just factor out, already if you know this equation directly, you could have written it straight, that it is A1 into bracket 1 plus beta theta. So if I'm to put in all these values, that means A2 is equal to, what is the original area? That is 12. 1 plus, now be careful how you write this, the area expansivity is 2.4 times 10 raised to the power minus 5, okay, times the change in temperature. I've said before, that was given as 100 degrees Celsius, okay, not 100 minus 20, that's 100 degrees Celsius. So I will say this times 100, then I can close this bracket and work this out. So this is what I'm going to input into my calculator, and I'm bringing in my calculator now. So I can say 12 into bracket 1 plus another bracket 2.4 exponent minus 5 times 100. I love, okay, I'm closing this first bracket and I'm closing this second bracket. I love putting my calculations directly like this so that the margin for error will be greatly minimized. I'm not arranging numbers and crossing them. I've done that on the formula already, so I can just input all the values for all the units that I'm trying to compute. So this is the expression for that, and I will press equal to. Now this I can convert to a decimal format by pressing the SD button. So this is giving me 12.0288. So I can say my area is 12.0288 centimeter square. Okay, and looking at all the options that we have, we can see this is option C, 12.0288 centimeter square. A lot of calculations, especially as presented in past questions, went ahead and used the linear expansivity directly in the equation, and they got this. And I can show you they are going to miss that. The correct answer to this question is option C. Two bodies of masses 3 kg and 2 kg are separated by a distance of 50 centimeters. We are to calculate the force of attraction between them. We are given the gravitational constant as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. So if you are to consider the two bodies, it is as shown on the board here, the 2 kg and the 3 kg bodies. Okay, so now we are told that the distance between them is 50 centimeters. So 50 centimeters, but we know for our standard unit we are supposed to use meters. So the distance D is 50 centimeters. Well, we know that is the same as 50 over 100 meters. So we can divide this 5 here 1, 5 here 2. That is 0.5 meters. So we can express the distance as this is 0.5 meters. Then we have to calculate the force of attraction between them. But noting that we are given the gravitational constant as G, which is expressed as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. Now, the formula that we normally use to solve for the force of attraction between two bodies in such a case like this is F is equal to G multiplied by M1 M2 over the square of the distance between them. So this is M1, 2 kg and M2 3 kg. So seeing we have all our parameters already, we can just go ahead to impute those parameters into the equation for our force. So we can have our F is 6.67 times 10 raised to the power minus 11 multiplied by the first mass, that is 2 kilograms, and the second mass, that is 3 kilograms, all divided by the square of the distance between them. So we have 0.5 raised to the power 2. So this is what we'll try and evaluate with our calculator. So if I bring in my calculator here now, you can say I want to express 6.67 exponent minus 11 multiplied by 2 multiplied by 3, but divided by 0.5 raised to power 2. So I can close the bracket for the denominator and check if I didn't make any mistake. 6.67 exponent minus 11 times 2 and 3 and divided by 0.5 raised to power 2. So seeing that I'm on track, I can press the equal to sign and I can see this is giving me 1.6008 exponent minus 9. So this is equal to 1.6008 times 10 raised to the power minus 9 newtons. Looking at the options, we are not seeing any in 4 decimal places, so we can do an approximation for this to be 1.6 times 10 raised to the power minus 9 newtons. So looking at the options, that means the correct option in this case is option A. Option A, 1.6 exponent minus 9 newtons. The diagram above illustrates an object moving in a circular path at constant speed. Which of the arrows indicates the direction of linear velocity? The question that we are being asked is asking for linear velocity. Normally there will be an angular velocity associated with such a body as moving in a circular path at constant speed, but that's not what we are being asked. And in this particular question, the linear velocity will be the one that Z is indicating. The other parameters we are seeing, this will be the angular velocity, this will be the centripetal force, but the one that is evaluating, that is indicating the linear velocity will be Z. Which of the following thermometers is used to measure the temperature of the human body? Now, not to be confused, what is used to measure the temperature of the human body is the alcohol in glass thermometer. But let's have a feel of what they also do. For example, the thermocouple is a thermometer that is used to measure the temperature for gas turbine exhaust, diesel engines, and industrial processes. So we can have this to be used for industrial processes, and is used for gas turbine exhaust. Okay. And then in the other case, we also have the gas thermometer. The gas thermometer is used for thermodynamics temperature. So this is used for thermodynamic temperatures and for meteorological works. That's basically the use of the gas thermometer. And then we're also seeing that we have the platinum resistant thermometer. The platinum resistant thermometer is unique in that it works on the fact that heat is directly proportional to resistance. So the platinum measures the change in temperature as a reason of its electrical properties, that the increase in heat will also have effect on the electrical properties. And it is used for high accuracy industrial works. So it's highly accurate, and that's why it's used for high accuracy industrial works. So out of all the options that we are given, the ones that is used to measure the temperature of the human body is the alcohol in glass thermometer. So option B is the correct option. In the diagram above, the time taken to trace a wave between P and Q is what? Is it 2 periods, 1 period, 1.5 period, or 1/4 periods? For us to answer this question, let's look at some brief understanding of the wave. For the wave that is drawn as shown, a complete circle is taken from the point of origin, let's say from here, from the point of origin here, to the complete circle, which is ending here. So from here to here, that's half a circle, but from the node to the node, that is a full circle. We have a maximum amplitude here, and we have the minimum amplitude here. So this is a positive half circle, and this is a negative half circle. So the combination of the positive half circle and the negative half circle makes a complete circle. So having that understanding will help us to look critically at this question and answer it correctly. But here, we are not starting the point from the origin. We are starting at point P. So what we need to look at is, where do we have a complete circle starting from point P? So from here to here, let me use that in blue. From this point P, okay, so here will be half a circle, up to here is half a circle, then here will be a full circle, and the time for one circle is a period. So from P to this point, this is 1 period, this is 1 period, and then we can see that the time that we are looking at is not stopping at that 1 period, it's looking to another circle, but from here that we have taken to here, we can see that that is a half cycle. So this is half cycle, and the combination of the two for us to reach point Q from point P is the addition of 1 and 1/2. So for us to evaluate that, we can say that the time taken is 1 period plus half period, and that will be 1.5 periods. And looking at the option, that is option C, 1.5 period. Which of the following materials does not serve as a safety device in electrical circuits? Look at the question we are being asked here. We are being asked that which of these does not, and they put that in bold letters, so we need to note that. So which does not serve as a safety device in electrical circuit. So if you are to look at the basic electrical circuit, just a simple schematic as shown on the board, we can see from this, let's say this is our source and this is our load. Okay, looking at all the options, all the devices that we have, this is the heating, and it provides safety from electrical shocks. This is a switch. You can see that the switch can help to disconnect the circuit. Like here, it is open, so there will be no current flowing through this simple circuit. But if it is closed like this, then current can flow. Therefore, the switch can serve as a means of protection, because once it is open, there is no flow of current in the circuitry. So the switch is a safety device. The earthing is also a safety device. What about the fuse? When we are talking about the fuse, when you look at your plug, generally, when you look at the plug, you have something like the live wire, there is a neutral and the heart, but there is always this fuse that is a small transparent tube with a strand of wire passing through it. What this fuse does is that if there is a high current going into the electrical socket, then the fuse itself will just, the wire in it will cut off. So it will cut off that high voltage that is coming in, so as to protect whatever device is plugged into the circuit. So out of all these options that we are giving, the connecting wire is this line that we are just seeing flowing straight through. So definitely at no point in time can the connecting wire serve as a safety device. It is the means of carrying the electrical power, of carrying the current, of traversing the voltage from the source to the load. So it's not a safety device, it's a connecting device, but all the other ones, they are safety devices. So the correct option out of all these options is option A. Which of these is not serving as a safety device in electrical circuit? It is the connecting wires. Which of the following liquids has the highest surface tension? Is it soapy water, cold water, hot water, or oily water? We need to understand what they mean by the highest surface tension, and that is a measure of the ability of these liquids to resist external materials from being easily permissible into them. Like for example, if you have cold water or hot water and you are putting another substance on top, what is going to be observed is that those substances that you are putting on top will easily dissolve into the water. The same thing with soapy water. But the oily water, if you are observant, the oil will tend to form a layer of protection. Okay, so if you say we are having something like a tube containing water, the oil will form a layer that is like protective at the top, so that substances that you are pouring will just tend to stay on top, meaning that there is a resistance from the oily water that is not permitting that substance, those substances, to easily dissolve into the liquid. That will not be the same in the case of cold water, hot water, or soapy water. Soapy water may offer some little resistance, but compared to oily water, that will not be the case. So the liquid with the highest surface tension among all those that are given is oily water. Option D is the correct answer. The nucleon and proton numbers of a neutral atom of an element are 238 and 92 respectively. We are to determine the number of neutrons in the atom. This question warrants that we understand how the nucleon, proton, and electrons of this question warrants that we understand the relationship between the nucleon and proton numbers of a neutral atom of an element. But for the case of explanation, let's consider the helium element in its neutral state. Looking at this diagram, we can see that the helium consists of 2 neutrons and 2 protons. So those 2 neutrons and protons are what constitute the mass number of the helium. So like here, we have the addition of neutrons and protons. That is what gives us the mass number. Whereas the atomic number is given by the number of protons. Electrons are revolving around the outer orbit of the helium atom, but we are not concerned about the electron here. We're only looking at the neutron and the proton. And the addition of the neutrons and protons will give us the nucleon. So you can see that from what we have in the question and are generally acceptable, the nucleon consists of the neutron plus the protons. Okay, that's what make up the nucleon. So we want to find, like in this question, we want to find the number of neutrons. Neutrons in that particular case will now be the nucleon minus the protons. Okay, so and here we are given that the number of nucleon is 238 and the number of protons is what? Is 92. So this is just what we need to evaluate from the question, and if we want to work that out, we can say 238 minus 92, that is going to give us 146. So here we have the neutrons giving us nucleon minus proton is going to be 146. That's option D in our question. So this is equal to 146, and it is option D that is the correct option from the options that we are given. An instrument used to measure relative humidity is from the options we are given, the correct option is the hygrometer. Okay, the hygrometer is the instrument that is used to measure the amount of water moisture, water vapor in the air. So that is hygrometer. But what about the other ones? The hygrometer is used to measure relative density based on buoyancy. So this is used for measuring relative density. Whereas the pyrometer is an instrument that is used to remotely measure the temperature of an object. So if you are looking at the corona case that is so rampant around the year 2020 year, what you notice is that the practitioners that are measuring temperature, they don't want to get close to the patient because they don't even know if the patient is susceptible to COVID or is already COVID infected. So what they do is they take this type of machine and they just point it at the person. Okay, so the person to be measured, maybe the person is just standing aloof and the person measuring is also not standing close, but the person will just use this pyrometer and beam it to the forehead of the person. So whenever you see that instrument, know that that is a pyrometer and used to measure the temperature, but it is done remotely. Okay, so what about the manometer? The manometer is generally an instrument used to measure the gas pressure. So that is it. If this question is coming out in some other case and they are asking which instrument is used to measure temperature remotely, you know that is the pyrometer. To measure relative density, that's the hydrometer. To measure gas pressure, that's the manometer. But to measure relative humidity, that is the hygrometer. The area under a velocity time graph represents what? Is it the speed, acceleration, moment, or distance? If I bring in a typical velocity time graph as shown on the board here, and we are to find the area under the graph, let's say we are to not look at the whole velocity time graph, just a section. So let me shade the section I would like to look at. Let's say we are to look at this section shaded. Okay, now we can see that that section that is shaded is pointing to the fact that this is a rectangle. This is a rectangle, and it has sides from A to B. This side AB. Let's say this is the length. Okay, let's say this is the length, and let's say this is from the point A to point D. This is the height. Let's say it's the breadth. We know that the area of a rectangle, is length times breadth. But what I want to actually draw out is the use of the unit to derive the solution to this. And what we will do in that case is that we have L in seconds multiplied by D in meters per second. So we have L in seconds, okay, multiplied by B in meters per seconds. Okay, so if we have to do that, what we'll do is this is L seconds times B meter per second. So we can say this is over 1, and we can say that the second will cancel the second. So the area is length times breadth, but the unit is in meters. The unit is in meters. It's these meters I want us to actually look at, meaning that the area under a velocity time graph is nothing but the distance, because the distance is what is measured in meters. If it is moment, that will be a totally different unit. Acceleration, that will be meter per second square. Speed, that will be meter per second without a direction. That cannot even be the case. So, looking at the option, I just use this means to explain out the fact that the area under the velocity time graph is nothing but distance. So, that is as shown on the calculation, and the correct option is option D. Which of the following statements about a neutral atom is correct? Before we consider the statements following this question, let's look at the atom in its neutral state. So here we have as a sample, we are considering helium here, and what we notice is that based on the model of the atom, the electrons revolve in the orbit around the nucleon. So the nucleon is this centerpiece, okay, this is the nucleon, and it consists of the proton and the neutrons. So looking at the first option, we are being told that the core is composed of electrons and protons. That would be wrong. Why? Because the core is composed of neutron and proton. Electron is in the outermost side. So that option A is definitely wrong. Option B, the number of electrons is equal to that of neutrons. Number of electrons, number of neutrons. No, for the neutral atom, they don't need to be the same. The electron may be far lesser than the number of neutrons, but that is not going to be the case in this option that we are being given, that the number of electrons is equal to that of neutrons. Then option C, the number of neutrons is equal to that of protons. Neutrons, protons, no, that is not the characteristics of the neutral atom. That has nothing to do with the neutral atom. So option C is also wrong. Option D, the number of protons is equal to that of electrons. Look at this. The proton is the positive charge of the atom. The electron is the negative charge of the atom. For the atom to be a neutral atom, those two numbers will need to negate themselves out, such that the atom will not be carrying either a positive or a negative charge. So option D is the correct option in this question. That which of the statement about a neutral atom is correct? It is that the number of protons is equal to the number of electrons. Which of the following properties is not exhibited by sound waves? So let's look at each of the properties that are highlighted. In the first case, diffraction. Diffraction is talking about a situation in which the wave that is coming, let's say this is the source of our wave, of our sound wave in this case, okay, let's say it's a mic, and then as the wave is coming, if we are to look at diffraction, we can say, let's talk about a window that is open, okay, an open window, and what normally happens is, once the sound waves get to the window, then it will be diffracted in such a way that it also starts being amplified, just as shown. So this is the reflection of diffraction, but that is definitely a property of sound waves. If you are to look at polarization, polarization is a case in which the sound wave is restricted in its movement. That is not applicable to sound waves. Ideally, the sound wave that is even emanating from the mic that we are using as sample can traverse in many directions, and nothing will stop it. If it's like an omnidirectional mic, it will just propagate in all directions without any restriction. But polarization refers to a restriction in the vibration of the source of the wave. So it can be polarization. So definitely polarization is the correct option. But let's also look at the other options. We can look at interference. Interference is a phenomenon in which some other waves will come to distort the particular wave we are talking about. And here, if it is sound wave, like coming from the source here, you can have, let's say you can have a vehicle that is moving along the road, and once the vehicle is also making some noise, maybe the horn is being pressed, and as a result of that, it can come out and interfere with the sound wave that is coming from the sound source. So interference is also possible with sound waves. And then let's talk of reflection. Okay, reflection when it comes to sound waves means that we are talking about echo. Like you have your sound source and it's going out. When it comes to a non-permeable surface, let's say a brick wall in an enclosed room, that wave will also be reflected back. So the reflection is what is going to generate what is referred to as echo. So out of all the options that we are given, diffraction is a property of sound waves, interference is a property of sound waves, reflection is a property of sound waves. That which is not a property of sound wave is polarization. So option B is the correct answer. When ultraviolet light is incident on certain metallic surfaces, particles are emitted. These particles are called what? Is it positrons, protons, photoelectrons, or photons? So let's say this is a metal with ultraviolet light incident on this particular metallic surface. So let's say this is our ultraviolet light. What happens with this ultraviolet light or photon energy E, where E is Planck's constant multiplied by the frequency of the ultraviolet light? What will happen is that if this metal has a work function W, but in the case in which the energy of the photon light is greater than the work function of the metal, then what's going to happen is that the electron, this electron here, is going to be emitted in such a way that it will move out of the metal surface, and it is called a photoelectron. Okay, so what happens is that this electron was emitted from here, and in being emitted, is emitted and its kinetic energy is given as the difference between the energy of the photon of light that is coming minus the work function of the metal. So in this particular question, the particles that are emitted are the photoelectrons as denoted in this particular explanation. So the correct option for this question is option C. Photoelectrons are emitted when ultraviolet light is incident on certain metallic surfaces, and the energy of the ultraviolet light must be greater than the work function of the metal. So option C is the correct answer. Niels Bohr drew certain conclusions about the structure of the atom. Which of the following statements is one of those conclusions? To answer this question, let's look at the model of the Niels Bohr atom, which is as shown on the board now, in which we have the atom, the nucleon at the center, and the electrons revolving in orbits around the nucleon. So in the option number 1, in the first option that we're given, here we are being told that the allowed orbits contain the same number of electrons. Looking at the model of the Niels Bohr atom, we are seeing that the first orbit contains 2 electrons, the second one contains 8 electrons maximum. Okay, so definitely the first option cannot be correct. They are not having the same number of electrons. We'll come back to option B. Let's look at option C. All the orbits represent the same amount of energy. That cannot be correct because looking at the formula for the energy level, En is equal to minus 1 over n squared multiplied by 13.6 electron volts. We can see that each of the orbits cannot represent the same amount of energy, because the first one, in this case, will have to be E1 is equal to minus 1 over 1 raised to the power 2, 13.6 electron volts, and let's say that is like minus 13.6 electron volts. Then E2 will have to be, now n is 2, so we have minus 1 over 2 raised to power 2, which is 4, times 13.6 electron volts. And that will be minus 4 in 13, that is 3, remaining 1, 4 in 16, that is 4. So these are not the same amount of energy, so definitely option C is also wrong. Looking at option D, we have been told that the orbit with the least energy is farthest from the nucleus. Let's look at that. Now, the orbit with the least energy means that that is the smallest. But looking at this that we just postulated, E1 and E2, we can see that E1 is less than E2. So E2, the one that is farther away, this is corresponding to n equal to 2. E2 that is farther away is more, because on the number line, the higher number will be less when it is negative, while the lower number will be more, because they are both carrying the negative sign. It's as if we are having, let's say we are having a number line, and you have 0, 1, 2, but here you have minus 1, you have minus 2, you have minus 3. So definitely the numbers here, they are lesser. The numbers to the left, they are lesser. The numbers to the right, they are more. So if we are looking at which number is greater, we can see that minus 1 is greater than minus 3. So minus 3.4 electron volts is greater than minus 13.6 electron volts. So the orbit with the least energy is not the farthest from the nucleus. The orbit with the least energy is the one closest to the nucleus. In short, it is the ground state. That is n is equal to 1. So definitely option D is also wrong. And that means that the correct option that is remaining here is only option B. That within an atom, there are certain allowed orbits. Of course, look at this. Here we have the first orbit, n is equal to 1. The second orbit, n is equal to 2. The third orbit, n is equal to 3. So these are the allowed orbits for the electrons of the atom in the Niels Bohr model of the atom. So the correct option is option B, that within an atom there are certain allowed orbits. The graph above illustrates the variation of temperature theta with time t for a solid that is being heated. We are not told the solid, but we just know that it is being heated. Which processes take place at segments P and Q respectively? So we are being asked what process is taking place as we are looking at this segment P and segment Q respectively. Respectively means that P first, then Q. So to answer this question, let's look at a typical modality that can help us. Let's say we are talking about the solid here that is ice. Just let's take that as an example. Now, on the scale that we're given, we have theta and we have time t. This is the origin of the graph. Let's say this is 0, and this is a negative number. Let's say minus 20 degrees Celsius, okay? And here, I will say this is 100 degrees Celsius, just hypothetically to explain this particular question. We can see that initially in this region, in this first region that we're talking about, here, in this region, that means we are still having ice, okay? That's not too clear. Let me just use the hint that can be seen clearly. Let's say we're talking about ice here. What happens between this point and this point is that the ice as a solid is being converted into water. So there's no change in temperature. So this is a change of state that is converting the ice to water, and that is happening at 0 degrees Celsius. So because we are only going to have the latent state of fusion of ice in place at that time, there's no change in temperature. So we can see that here change in temperature, change in theta is 0. So the heat is only being used to convert the ice to the water. And then moving to the right region here, what we have in that particular case is definitely we are looking at water, because from 0 degrees Celsius, the temperature is increasing with time. Is increasing with time to such an extent that when it goes to its boiling point, so definitely that means that here on point Q, the temperature of the water is not increasing again because it has gotten to its boiling point 100 degrees Celsius, and so we are just having the water boiling, and that is all there is to the question. So looking at the first option, we have that as freezing and vaporization. No, that's not what our explanation is telling us. In the second option, we have evaporation and solidification. No, that's not what we are also coming up with. In the third option, we have melting and boiling, and I think this is the correct option, because initially it's a solid at 0 degrees Celsius for a time, for some amount of time. The ice is just being melted from solid to liquid. Then when it gets to the liquid and we continue heating it, so that is being indicated with this straight line, okay? And then getting to point Q, already the water is boiled and is just at its boiling point, and then we have boiling taking place because that's 100 degrees Celsius in the case of the water that I used to explain. Of course, definitely is not condensation and evaporation. It's not moving from the liquid state to the solid state at point P. So looking at all the options, the correct option is option C. It is melting and boiling. And with that, we have come to the end of this wonderful journey of solving all the objective questions from the 2019 Physics Objective Exam paper together. The journey has been wonderful. Thank you for staying tuned like this. There is only one thing else I'm expecting from you if you have not done it. I want you to go ahead and subscribe to our channel. And the best feedback we can get is by your subscription. So please take a minute. It's free of charge. Go ahead, click the subscription icon, click on the notification bell so that whenever I'm uploading a video, you are going to get that video instantly. And furthermore, I want you to share with your friends. Do you know anybody that is having some challenge in any area that we're actually addressing on our channel? We want you to also share with them. Let's build this academic excellence in students, and together we can make impact. It's Day 2 Academy, and until next time, God bless you.